So last time, what we did was a little bit of compressor, talked about nozzles, diffusers, that sort of thing. Today, what we're going to really quickly touch on is a pump, although pumps are solved fairly similarly to... okay, so they're not solved in this chapter. They're solved a little similarly to compressors, right? But later on, they're solved a bit differently. And so we essentially, just for right now, we're gonna try and think of them more as compressors rather than anything else. They solve very similarly, but later on, they are a bit different. And so let's kind of just, we'll go through it very quickly about essentially how you do it. So for example, this is a question. We're not going to actually do the question, but this right here, number one, if you see this question, which by the way, I know some of you probably have already, since you turned in the homework already, you know that this question is very similar to the last one. You see it went up in height. So this question right off the bat tells you that there's a potential energy effect. And they've also given you some other things, right? It tells you to find the velocity, so obviously there is some velocity considerations. And right here is the pump, right? So as you guys can see here, so this is the working equation for the pump. We're not going to deal with this right now, this stuff, because this is mv over a. We've already talked about this equation for velocity. But as you can see, the equation is pretty much the same, right? They remove the heat transfer, right? Because, wait a minute, introducing. Oh, did they say something in the question? Let me say something. Oh, okay. The magnitude of the rate of the heat transfer from the pump to the surroundings is 5% of the power output. So they were able to remove this right here. Essentially, Q we know is 5% of the power output, and so they were able to substitute that in, more or less, and it solves the exact same way as before, except right here. This is the important part of pumps, okay? The important part of pumps is that enthalpy, the change in enthalpy is equal to the work, right? Which we can assume, which we know that was same for turbines and same for compressors, right? If you neglected velocity and potential energy. But if you noticed here is that this is now the equation. The change in temperature is equal to V sub F, which is the saturated liquid value of the fluid of T at the temperature, times the change in pressure. So this essentially is V delta P, right? So this right here is an equation you will see quite a bit in the next classes, and this is how you solve from pumps. This is what you would call what I like to call the perfect pump equation. So essentially, the work of the pump, or yes, the work of the pump, the delta H of the pump is equal to, you can rewrite this as this. So it's the pressure before minus the pressure after, right? And then it's multiplied by the V sub F term. And what V sub F would be, it would be at 1. So it would be this volume value at this temperature. And this gives you the perfect pump equation. And so basically work can be rewritten as this. That's what I wanted to touch on. And if you do happen to have a pump, I will make sure that this equation is written down. But I think it's in your equation sheet. I'm fairly certain. But this is what I wanted to touch on. They solve the exact same way. You write this out, you find what you know, but only just know that the delta H can be rewritten as this. So that's the big difference between them. But today what we wanted to talk about, the main subject of today, was heat exchangers. So this is one of the last processes that we could go through. So we went through compressors, turbines, pumps, nozzles, diffusers. And so now we have heat exchangers. And then there's one more after this one called throttling devices, or valves, as you might know them. So it says heat exchangers have innumerable domestic and industrial applications. This is true. You find them basically everywhere. basically everywhere in society, like in your house, definitely in air conditioning systems. And then it says also in automotive, electrical power generation, definitely, and chemical processing. Indeed, nearly every area of application listed involves heat exchangers, so that is true. It says one common type of heat exchanger is it is a mixing chamber in which hot and cold streams are mixed directly in figure. So we've already seen this one to some degree. I think they show it though. No, they don't. It was in 413, maybe later. But we've already done a question like that, right? You remember the two streams mixing in that one chamber and one chamber leaving, or one exit leaving? That was a mixing chamber, essentially. And it says the open feed water heater, which is a component of the vapor power systems introduced in Chapter 8, is an example. We did this question, an open feed water heater. Another common type of heat exchanger is one in which gas or liquid is separated. So this is a non-contact heat exchanger, right? So there's direct contact and non-contact, right? So it's separated from another gas or liquid by a wall through which energy is conducted through. These heat exchangers are known as recuperators, take many different forms. We have counterflow, parallel tube within a tube, crossflow. There's a bunch of these, right? Like, a bunch of heat exchanger types. And I don't know if anyone in here has taken ME 302 yet, but you get into what each one of these does, like specifically, like why you use them. But in this class, we're more focused on the entrance and the exit and like the differences between the two. That's like where we're at. So, heat exchanger modeling. So it says, as shown by figure 413, I'm actually going to go find this because I'm kind of getting annoyed here by where they're showing these pictures at. I wonder why they're like so far down. Or if I missed it already. 413. Yeah, like this is... They're saying show pictures, but they're not even in the same chapter. Okay, whatever. This is really dumb. But anyway, essentially, we'll show you how to draw them a little differently here in a second. But obviously, they didn't think that far ahead just to put them in the same chapter. So, although this is what they look like. On paper, this is generally what they look like right here. That is a big blob. So, they generally look like this. You get conditions 1 and conditions at the other side, so 1 to 2, and then 3 to 4. You number them like this, and you do this ones, you get all the properties here, and you get all the properties here, right? Is this figure 413? Is that one someone's going to tell me? But essentially, this is what they end up looking like. A lot like this. Is it really? Maybe you're right. Oh, you're right. Okay, so this is the different types. Thank you for pointing that out. So this is one that we've already seen. This was that mixing chamber question that we already did. This one is, so this is cross flow, and this is tube within a tube, and then you have tube within a tube parallel. So one of these is counterflow, and this is concurrent flow or parallel flow. And each of these two actually have different properties, right? Like they actually can do the heat transfer a little bit differently. These two right here. And these are non-contact. So essentially how these work is that you have them flowing in here. So this would be a cold liquid or something. Let's just say that it's a cold liquid. And in here, you would have hot, right? More or less, inside of this cross-section. So essentially, if you look at this, it looks a lot like this. So you would have cold here, hot here, right? And then it would transfer in through it, right? They're actually within each other. That's what they mean by same tube, whatever they actually called it. It was like same circle or same tube. But let's get back onto this. So it says, as shown by figure 413, heat exchangers can involve multiple inlets and exits. For a control volume enclosing a heat exchanger, the only work is flow work at the places where matter enters and exits, so the work CV term drops out. It's very important. So in a heat exchanger, it's pretty obvious that a heat exchanger's job is it's not to do work, right? It's not to like turn a shaft or, raise a weight or, compress some sort of liquid. That's not its job. It's just to simply transfer heat. That is the only job of it. So there is no work of the control volume, right? That part goes away. So it's 0, right? Obviously, since heat transfer is a part of the, like what it is, what it's doing, this is going to stay. I think you guys could have figured that out. Heat transfer will stay because it is a heat exchanger, so obviously some Q will remain. And then we have the rest of it, right? So the rest of it here, we have inlet enthalpy, inlet velocity, inlet potential energy, and then exit of the same thing, right? So does anybody think that velocity is going to be really massive? Is it going to be notable when compared to the amount of heat transfer we get from this? Does anybody want to take a shot at that? You think it will be, is it notable? Is it something we can remove? And yes, you could read the screen and figure this out, I'm well aware. But I'm liking you guys to use your noggins here. Yeah, so delta V is something we can get rid of. And so here's the reason why. Is that when you enter one of these heat exchangers, right? Like when we enter one of these, our goal is to transfer heat, right? So what would be the point of sending this fluid in here going, 100 miles an hour when trying to transfer heat? You see the point is that it would not transfer very much, because remember, heat transfer is a function of mass flow rate, temperature difference, but there's also velocity, right? If you there's not enough time for it to even touch the heat or like get the heat to conduct into it, it won't ever actually transfer it. So you'll get very little differences. So essentially, velocity is something that we can get rid of based on when you enter this device, our goal is to transfer heat, and if you send it through here really fast, it doesn't have enough time to absorb as much heat as you want. If you send it in here relatively slowly, it will, from this entrance to this exit. Now, okay, it also depends on how big your device is, right? So, like for example, if it's a small device, you want it to do multiple passes, right? That's why I think radiators have multiple passes of the same heat exchanger. But if it's something really big, you could send it through there, I guess decently fast, but it's just because of how big the device is, right? Essentially what you want is you want your fluid to go through here, and you want it to pick up the energy that is, or get rid of the energy that it has in its mass. And if it goes through there too fast, it won't. So, but yes, it will not be very much. Velocity will be fairly small. And obviously, potential energy, we're not going to have this thing start at a lower altitude and go higher to transfer its energy. It doesn't really make sense, right? So we can get rid of that. So these two will drop out, both of them, and then you are left with Q is equal to, essentially, the following. So it'll be Q is equal to M H1 minus H2. And now this is for one inlet, one outlet. So if the steady state conditions, Q will be equal to just the change in enthalpy, right? So this shouldn't be that difficult, right? So I think everybody's probably got a good handle on that. And so then we have applications to power plant, condenser, and computer cooling. So actually, since my computer is next to me, I'm sure, and it's probably a lot of you have your own nice computer, I'm sure, maybe. You probably know how a lot of these things work. But specifically, I know, so condensers. So we've talked a little bit about how condensers might work. It is a heat exchanger. They exist in your refrigerating cycles. They also exist in power plants. And they do the same things in both of them. So for power plants, what the goal is to, when you come out of a turbine, so I'm actually going to draw a little bit of a schematic here. So this is a boiler, right? So that's a boiler. And what happens is that from the boiler, there are probably many operations in between, but like for the most part, the major operations are, and this is going to be turbine, right? So when it comes out of the boiler, it is really hot, high pressure, and when it goes into the turbine, it turns it turns most of it, which spins the turbine blades and creates power, right, work. And then after the turbine, for this cycle to continue, because we don't want this to just happen once, right? We don't want to replace this fluid every time. Well, what just happened? Did my screen just die? Okay. Yeah, it's back now. Sorry about that. I don't know what just happened. But essentially, we don't want this to just happen once, right? We want this fluid to continue to come around this cycle. Because think about it this way. Think about if this is what we did. Think about if we pumped that right here. So, because that's how it gets to high pressure, by the way. We get it to pump, right? We pump it back into where it needs to be. So I'm going to draw a pump down here. Could you imagine if this is what we did? Is if we just shoved in a bunch of water, we pumped it to the pressure we wanted, we sent it to the turbine, and then it just leaves. We'd have to continuously throw in new water every time or new working fluid because it would just leave, right? We don't want that. We want this to be a system where it will continuously do the job, right, with the same fluid. And how you do that is that pumps can only be run when everything is liquid, right? And since this is water in the cycle, we need this to be liquid when it reaches this pump right here. And so how do we do that? Well, how we do it is we use a condenser. And what happens in the condenser essentially is a bunch of it runs essentially with lake water. It does a heat exchanger pass with some other fluid, and it just removes all of the heat from it, and it gets it down to saturated liquid, which is a 100% liquid value, right? We all know that x equals 0, is saturated liquid on the tables. And it means really liquid. There's no vapor in it at all. And so essentially this right here would be the condenser. And so it condenses. Most power plants have their own water supply, which is like the one in Lake of Egypt, has its own man-made lake that it runs this with right here. And so when it runs through here, it does heat exchanger passes with a bunch of tubes. And essentially the condensate, which is why it's a condenser, falls out, right? The condensate leaves, right? And essentially what you get here is you had right here is still high temperature. So T2 is still pretty high. Pressure 2 is still, it's low. It's definitely low. It's low. Okay, it's as low as it's going to get in the cycle. It's going to be probably close to atmospheric pressure. But then when it gets here, temperature is going to drop, right? Or not temperature. Quality is going to drop. Sometimes temperature will drop, but every time quality will 100% drop. It will go from quality of, let's say 0.95, which is a lot of vapor, all the way down to x equals 0, which is all water. And remember, because these two are both have a quality, their temperature are the same. So that's why temperature doesn't always drop. Sometimes if this is still superheated, temperature obviously drops. But for this part right here, x equals 0, we are now all liquid. And therefore, we can now enter the pump and get back up to where we want it to. And so that's basically the goal of these cycles, right? That's the goal of a condenser, and that's a heat exchanger process that you find in many different applications. Radiators are similar of how you want it to work, at least. Let me see if they just went on to a question. Okay, so they just went ahead and did a question. I'm going to talk about the next one here, which is computer components. So right now, my computer next to me is water cooled. And so essentially all it does is that it has like a touch plate. It has like a copper plate where you stick this thing attached to it, and you attach it. And what happens is that water runs in a closed loop from the fans, and it essentially runs to the copper plate, and water directly contacts the plate right over the CPU. And essentially it takes that heat. So it touches the contact, and it runs it back towards the top where it has fans to blow air across the now hot water, and then it shoots it out of the top, right? So that's how computer parts work, especially this one, right? And then there's other ones like where you can just get fans to blow across it and get rid of it. But the whole point is that what you want is that you're just trying to take heat away from something that gets very hot. And so this right here is what they're talking about. But let me see. We're going to do the next part, and then I'll come back and do a question. on something like this. Probably going to do the condenser one, not the computer device one. So basically, let's to recap, heat exchangers, their only goal is to exchange heat. They create no work, and also, I mean, they're used in all sorts of things. You'll see basically all over the place. And yeah, it's more or less it. The equation kind of reduces to something really easy at the end. But then we have throttling devices. So throttling devices, it says a significant reduction in pressure can be achieved by simply introducing a restriction into a line through which gas or liquid flows. This is commonly done by means of partially open valve or a porous plug. So what this one is saying is the following. Let's say we have a pipe here, right? Right? Let's say we have a pipe here. This right here, is just a open, straight, okay, not straight pipe, but you get the point, right? It's sort of straight. And it is just a normal one. But then if you want to restrict flow into the next pipe, you have something like this, right? This valve can, close a little bit. It can open a little bit. I know I drew that kind of poorly, but essentially that's the point. The point is that something can throttle how much gets through, right? Like bottleneck it, essentially. And so you can have a valve. This is something you'll see a lot in not heat exchanger devices, but I guess heat exchanger. Refrigeration cycles have a valve in them, and a lot of things have valves in them. But essentially, what it's doing is that it's just throttling how much mass can enter at one point, and so that is their job. And what they actually do in practice is that it drops the pressure immensely in a hugely irreversible process, which we'll get to later. And so these throttling devices are put in figure 415. So let me go and find that right here. So this right here is the valve, right? So essentially you would suggest that if they pulled this all the way up, it would be open, right? It goes through here. But then as you drop this down, and it only lets a little bit through here, so let's say instead of where it is, it goes like this, right? My pictures are bad, I understand. But let's say it did that. Now mass can only escape through a little part of this, right? So it bottlenecks it. And then this one, I don't really know much about this, but I know what it does. Essentially, this is just a plug of the thing, but since it's made of a porous material, mass passes through it, but not as much as it would without it, right? So that's kind of how this one's going to work, but I've never seen one of these. I have seen something like this, though. These are probably, and there's many different types of valves, too. Like this one, this isn't the only one. So it says, an application of throttling occurs in a vapor compression, this is refrigeration systems, where a valve is used to reduce the pressure of the refrigerant from the pressure at the exit of the condenser to the lower pressure existing in the evaporator. We consider this further in Chapter 10. Throttling also plays a role in the Joule-Thomson expansion, considered in Chapter 11. Another application involves throttling calorimeter, which is a device for determining the quality of a two-phase liquid-vapor mixture. The throttling calorimeter is considered an example 4.9. I don't think I've seen something like this. Not in our. Just to let you in behind the curtain, there's a 401 lab that exists later in your time at SIU. That you use a refrigeration cycle to take data. You actually watch it operate, and I'll go ahead and so basically what ends up happening is that the throttling device, there's three different throttling devices, and the one that we use is there's pure mechanical ones. There's just one like this. And then there was like a gauge one, which I actually found the pure mechanical one to be really cool, and we'll talk about that in just a second. But essentially, how this refrigeration cycle works is that you have evap's at the bottom. Sorry, pardon me. I always forget. So this right here is the condenser, and how a valve is drawn on paper is like this generally. And then down here is the evap, so I'll draw that. And you'll do a lot of this in thermo too, by the way. And then the compressor is right here. So there's two heat transfer processes. one work required process, and then this right here, which is the valve. And how this ends up working is that it goes like the following, is that on a TS diagram, I guess you could say, we will have something like this. So 1, 2, 3, and then 4. And how you would number it is 1, 2, 3, and 4. So what the job of the valve is that, so this right here is a high pressure, the highest pressure in the cycle. It's at state 2, right? Because after the compressor, you would imagine that this is the highest pressure, right? It has to be, because it's a compressor. It raises the pressure. That's what it does. So when you go up here, you are now at the high pressure of the cycle. And for this cycle to work, it now has to get back down to the low pressure, right? Once again, the same example applied to whenever we did the other cycle, the power one, is that if we just got rid of it here, we'd have to keep inputting more at this low pressure. And it doesn't work like that. We want this refrigerant that runs through here to just continuously run until we have to change it, right? And so from 3 to 4, it runs through the valve. And what the valve does is that it essentially just drops the pressure down. Runs it down all the way down to where we had it before, which is the pressure of state 1. That's the job of this. So this is what it ends up looking like on a TS diagram, so temperature and entropy. But we haven't talked about entropy quite yet. But this is what you would use for that cycle. So you will use this, though. This is something that you'll see in the next class. And so, for so then we'll talk about, I guess, this equation for it. By the way, like valves, you don't have to do this for it, like, ever. So, I don't think I've ever actually done a energy balance on a valve. But it says, we'll just do it anyway. It says, for a control volume enclosing a throttling device, the only work is flow work at locations where mass enters and exits the control volume, so the WCV drops out of the energy rate balance. So, that goes. There's usually no significant heat transfer with the surroundings. And it says, and the change in potential energy from inlet to outlet is negligible. Agreed. Thus, the underlying terms are the ones that stay, right? Right here. So it's sort of like, it ends up being just like your, the equation for the diffuser and the nozzle. It ends up being the same thing. But they're designed to do two massively different things. Alright, so let me see if we can get... Alright, never mind. So let's see if we can do a question. So we have 30 minutes or 20 minutes. Let's do a question really fast. There wasn't a whole lot in this chapter about like what these things are like really about, but I guess I should show these. So we have evaluating performance of a plant condenser. So this is our question. So we are going to be using a power plant condenser here. So a power plant condenser, as I told you guys, is cooling water, runs through into the steam. So as you can see from this schematic here, we have steam, we have condensate. So this right here is the power plant. So this is the one that just got taken out of the turbine and the boiler, right? So that is here. I'm hooking it up, right? So that left here. And then condensate exit. As I told you guys, condensate is what happens after the liquid condenses, right? So we become full water. That's what condensate, if you ever see a question that tells you condensate exits, it means it's water. Just all water. So right here is the steam, which is the working fluid of the power plant cycle. And right here is the lake water. So this right here is where the lake water comes in. So whenever power plants are built next to lakes, this is what they use. They use a lake water. That's the only reason they're there. The only reason that they're next to a body of water is for this. It is for cooling water to go in and cool this steam off to make to essentially get it down to condensate. That's the only reason it exists. So right here, we now have to start the question. So I will pull up a good old Paint 3D, our favorite program, and then we can work on the question. So, as we do always, we take things down little by little, and we do a little bit of work as we do it. So let me go ahead and see how this is going to look. That is big numbers. Yeah, it's because I'm zoomed in like hell. Alright, so let's start this right here. So, these are the things that were given in the question. So let's do knowns here. So it says the first one. Steam enters the condenser. So they've told you it's water, essentially, but it's steam. Enters the condenser of a vapor power plant at 0.1 bar. So we are under atmospheric conditions here. So we have pressure 1 is 0.1 bar. And a quality, so they've given us a quality of 0.95, okay? And then it says, and condensate exits at 0.1 bar and 45 degrees C, okay? So now we have some other things which we will move to. So we were given the same thing. We were given P2, which, by the way, generally across a thing like this, pressure doesn't generally change. So that's something that you could also hold on to. And what else did they give us? They gave us a X2, so the quality at state 2 of 0, right? Because it's condensate. Remember when I said condensate means that it is water. And they also gave us that T2 is equal to 45C, right? Now, they've given us something else. So here, I'm actually going to section this off here. So this is steam. So this is the steam part. And this is cooling water. So this is something that I think you should do. You should section off what you know about each fluid, because if you interchange the two of them, you'll get confused. So it says cooling water enters the condenser in a separate stream as liquid at 20 degrees C. So we were given T1 CW. So T1 of cooling water, or you can call it T3. I'm probably just going to call it T3 for just to help. So T3 is equal to 20C. And they also said that X3 is equal to 0. Okay? And then there's something else they've given us. They've given us the next thing where it says, and exits as a liquid at 35C. So we have T4 is 35C. And they've also given you that it's still a liquid after there. 0. It could be subcooled, but remember, we approximate at the temperature, guys. So if you recall that at the temperature, you just look these values up. I'm just going to call them X4 is 0, but it could be subcooled, but the way we do it doesn't change. It will still be at the temperature. You look up the enthalpy values. So it doesn't change how we do it. So this is what we were given. It says heat transfer from the outside of the condenser and changes in the kinetic and potential energies of the flowing streams can be ignored. For steady state operation, determine the ratio of the mass void of cooling water to the mass void of the condensing steam, the rate of energy transfer from the condensing steam to the cooling water in kilojoules per kilogram of steam passing through the condenser. So a lot to unpack there, a lot to unpack. So let's do this one first. So I'm going to move this up. A lot to unpack. So what we need to do is we have to do some things, but to find mass flow rate ratio and also the heat transfer. But before we do that, let's get back to what we do best, right? What we do best is we start at each state and we just work from there. So let's start there. So let's start with the steam. So this is the steam, right? So steam is right here. What we need to do is we need to find everything we can about these values, right? What do we know? So what we can do here is, let's go to the tables, right? And if we go to the tables, what we will find is that we will see pressure 1 is 0.1 bar, X1 is 0.95. So that means we need to go to the saturated tables immediately, and we need to go to 0.1 bar right here. 0.1 bar. And our quality is 95%, which means we need to find the actual enthalpy value that we need here, right? And so our enthalpy is somewhere between these two values, the liquid and the vapor. It's closer to the vapor, I'll agree with you there, but we don't know exactly how much. So we have to do that. And how we do that is the following. We do H1 is equal to HF plus X plus X1 times HFG. And HFG is the difference between HG, the vapor, and HF, the liquid value. And how you do that one is, now you have 191.83, which I think I recall that's what that was. 0.82. I was close. Oh, no, it is 83. I was looking at the liquid value for internal energy. So 191.83, and we have 2392.8. 2392.8. If I got that wrong, let me know. Yep, okay, it's good. And you will get a H1 value of, well, this is where every single week I say I'm going to bring a calculator. Someone remind me after the class to bring my calculator. $24 something. 2464. 2465. We'll just call it that. Yes, that is basically right. All right, so we have now found that H1 is equal to 2465 kilojoules per kilogram, okay? Now we need to find the exiting state. Well, this one is pretty straightforward, right? The exiting state, you have pressure 2 is 0.1, and T2 is 45. So what we should do is we should go right back to the tables. So here, you guys will notice, if we look at these tables, is that we are at the same pressure, and it said that our temperature is 45 degrees. What are we? What state are we in? Are we saturated? Are we superheated? We subcooled? What are we at, guys? Anybody know? Using this what I have circled. Temperature 2 is 45 degrees. We are subcooled, that is correct. But because we know a temperature, and we approximate values in the table, we're going to then go use our temperature value at 45, which is here, 45, and we will go across to the saturated vapor or liquid value, saturated liquid value, and we will grab our enthalpy to be 188.45. So let's go back. So right here, H2 is equal to HF at T2, which is equal to 188.45, I think is what I said. But if I get these wrong, I apologize. I'm pretty sure that's right, though. Yep, okay. So what I've said here is that the enthalpy of 2 is equal to the enthalpy of the liquid value looked up at the temperature, not the pressure. So HF at T2 is equal to this. Okay? So we've now found everything we needed to know about this right here. Fair enough. Straightforward. Now, let's move into the water. So let's do cooling water. So we know that T3 is equal to 20 degrees Celsius and X3 is equal to 0. So once again, this is just a liquid value that we can look up at the temperature. So we're at 20 degrees. And it looks like 83.96 is our value that we're looking at. So let me go back here. So H3 is equal to HF at T3, which is then equal to, oh my god, I'm going to have you guys write these into the chat every time, 83.96. I need you guys to be my scratch pad. Alright, and then we also have H4. So H4 is then equal to, once again, another liquid value, right? Because it's cooling water, and it's not boiling, clearly. But you go look this up at the temperature, 35 degrees C. So let's go look it up at the temperature again. 146.68 is what it is. So 146.68 kilojoules per kilogram. So we now have the cooling water and we have the steam. All the values of both of them that we need, right? And that's all the ones I think we need. But we might need one here in a minute anyway. But we'll find out. We might need more. But I don't know if we do. So, but these are the enthalpy values, right? These are the ones that are important for heat transfer. Because if you recall, now we get to write our overall equation, right? So let's write our overall equation. So let's do steady state equation for heat exchanger, right? So let's do that. So let's do this. Steady state equation for heat exchanger. I don't even know why I wrote that. It didn't even change like anything. I was trying to be hip. What do you want from me? So steady state equation for the heat exchanger. So let's write this out. Q minus W plus M. I'm just going to call it M1, but it doesn't, they're the same mass flow rate, times H1 minus H2. And they also said that kinetic and potential energy effects are negated, right? We don't need to take these into account. So this is what we're left with, right? From the equation prompt, or the question prompt, this is what we're left with. So, what goes away? Well, I'm glad you asked. I don't think you did, but this goes away, right? Work of the control volume goes away. We're not spinning any shafts or anything, right? So, what this is left with is the following. We are left with, let me go ahead and write it down here. We're left with Q is then equal to, although I have so there's inlets and outlets here. So actually this equation actually is a little more complicated. I was thinking about doing it so there's two ways you can do this, but yeah, okay. So this is fine. So I'm only looking, so really fast, what I'm only looking at so far is I'm only looking at this. I'm looking at the heat transfer that this is giving to the water, right? I've only written 1 to 2, right? Does that make sense? But there's two equations you can write here, and we'll show you that in just a second. So I'm actually going to back this up really fast. So we have this is the first one. And let me add something to it, equals 0, right? That's the first equation you can write for a heat exchanger. The second one is the following. It's the total heat transfer, which is the following equation. It is M1, right, times H1 minus H2 plus or minus, depending on how it goes. But I think, let me see how I'll write this. H1, so that's fine. So that is, this should be so H2 minus H1 is equal to M1 times H3, let me see, H3, nope, it should be H4 minus H3. I am fairly certain. Let me see, H4, so that'll be a positive, and this will be a negative. Okay, so this is the total heat transfer equation, right? Because if you guys think about this, this has to be the same, right? Any heat transfer leaving this fluid right here has to be picked up by this fluid. Would you guys agree? Because remember inside of here it says heat transfer from outside the condenser and changes. They've said that heat transfer from outside is gone. Essentially, we're saying that any heat transfer that takes place goes from one fluid to the next, right? So we know that all heat transfer from this fluid has to be picked up by this one. And what that means is that they are the same heat transfer, but they are opposites. Okay? So that means that any heat that is gained by the cooling water from the condensate, essentially it's either lost or gained, right? Depending on the direction you want to go. And so, from here, it is lost. Heat transfer is lost in the steam stream. Lost. From the cooling water stream, it is gained because it is cooling. It's going up in temperature, right? It's trying to take away the heat. Okay? So this is the total heat transfer equation. So essentially it is more or less the heat transfer from the first stream has to be equal to the heat transfer to the second stream. Does that make sense? Say something if it doesn't. Okay. I'm glad it makes a bit of sense. So now we can scroll down here, and since they've already said it's steady state, although I've made a mistake here, a slight one. Not a too big though. I will change it. I didn't write. I made a mistake there. So, and the mistake that I made is something that I probably will see. You'll probably see a lot of mistakes like that, and I hope you don't do them. But essentially what I did was that I wrote the mass flow rate for the one stream, but it is not necessarily, it's not actually the same for the other one. And so that's why I made a mistake. So M1 and M3 are different, but M4 and M3 are the same. So essentially, I'll go back here. So the mass flow rate from this stream is the same, and the mass flow rate of these streams are the same, but they are not equal. These two are not equal. So that's what I made a mistake. I actually wrote that wrong. I wrote that they were all the same mass flow rate, but they're not. So M1 times H2 minus H1 is equal to M3 times H4 minus H3. Okay? Now, in the interest of time, we might have to slide down here. And so, what you are left with is what we have right now in the equation, right? Although they have it the opposite way. They have it as M1 times H1 minus H2 plus M3 H3 minus, and that's because they have it all on one side. I don't think I do. I have it all. I have them equaling each other, so it changes it. That means that it's just opposites. It flipped. So we have the same equation as them. Now, one of the questions in there was to find the ratio of masses, right? That was the main thing, was to find the ratio of the mass flow rates. So the ratio of the mass flow rates would be the following. It would be, I think, which way did they ask it? Let me see. Determine the ratio of mass flow rate of the cooling water to the mass flow rate of the steam. So cooling water to steam. So we have to have M3 over M1 has to be equal to what? So if you move over M1 on the other side and divide by the other side, you will end up with the following. H2 minus H1 over H4 minus H3. Right? Let me see if I did that right. Move this over, move that over. Yes, okay. Makes sense to me. So this right here will be the ratio of the mass flow rates, right? And I don't know if that's the answer they wanted. That's all they wanted? Yeah, that's all they wanted. Okay. So they get, which I'll do the numbers for in just a second anyway, but they get like 36 from this. But in the interest of time, we might just have to take their word for it. I usually don't like to. But essentially what it is that you drop your values in here. So it's 2465 minus, H2. 188.45 minus, although this is going to be, we're going to flip it to an opposite here in a second. But just hold on to that for a moment. I'm not going to post my PC specs, I'm afraid. 83, and then it's H4, so it's 1. Actually, I should do it the opposite way. I'm going to manipulate. Okay, so since I know how this is going to come out, I'm going to manipulate the equation just a little bit and change the sign of it while I'm doing it, because that's just what we need to do. So if you do this right here, I'll do it on here, and hopefully we will just do 188.65 minus 45, whatever. Same difference. divided by parentheses 83.96 minus 146.68. And you get 36.3, which I think that is exactly what they got. Yeah, they got 36.3, which is right here. And all I didn't do anything like super, big brain. All I did was, because I knew that this ratio was going to come out negative, and you can't have a negative ratio of masses, because then you'd have mass like not even entering. So I just flipped the sign of the bottom one to get two negatives. That's all I did, because I saw where it was going. And this is just as a result of me not knowing the right signs to do. So, and this will be in 0.3 and this has no units, because it is kilojoules per kilogram divided by kilojoules per kilogram. And remember, since this is a ratio of masses, that makes sense, because the ratio of masses also has no units, right? So this makes sense. Now, the last part of the question asked for the following. It asked for the heat transfer, right? And so really fast, this is something I need to nail into your heads, is that from this first equation, or from this second one, this is what I meant right here. For this second equation, the M1 times H2 minus H1 is equal to the other mass flow rate times H4 minus H3. You cannot get a heat transfer from this number. From this, you cannot. The reason is because from this total equation, what will this say? If you solved this, what would it give you? It would give you 0, right? It would say this heat transfer is equal to this one, right? But, if you solve this one, just one stream over here, if you solve just one stream, you will find out how much heat transfer is going one direction, right? Like the band. It will be going one direction, which means that you need to use this one. So basically those two equations, they draw the system differently. So I'm going to draw the one that we're doing now. Is this one. It only takes into account inlet 1 and outlet 2 and this first stream, right? But the second equation is the total one, and this is something you have to know for these types of questions, is that there are two ways to draw the system. One is for one stream or the other stream, and then one is for both of them. And it gives you two separate equations. And so the equation we have to use here is we have to use the one stream, the ones that they're separated on. One stream. And what that one stream will do is it will give us a number for heat transfer. And so, very simply, you just do Q is then equal to M1 times, although we don't have a mass flow rate number, so I'm just going to write it there, but you would divide. So essentially it would be the following. It would be Q divided by M. So Q per mass is equal to H1 minus H2, or H2 minus H1. And then that number, so Q over M is then equal to, looks like we're gonna have to do this one again. Calculator's riding again. 2465 divided by 1, or subtract 2465 minus 188.45. And you get this as a heat transfer per mass. So it is 2276. And you get 2276. And this is kilojoules per kilogram. And I'm fairly certain that that is what their answer is. I will go look though to be sure. Yep, right here. Which I think that's what we got. Yep. And so this is the heat transfer leaving. And so really fast, you guys can do this either way. You could have written H1 minus H2, and you would have got a positive value here. It would have been a plus 2276. But you would have to know, just based on your own, your own knowledge, your background information, you would have to know that this heat transfer is not gained. It is not being gained here. Because if you go back up here, the steam is losing heat, right? The cooling water went from 20 degrees Celsius to 35. It didn't do that by losing heat. It did it by gaining heat. And it gained it from the steam. And so that's why you have to be careful with the way your signs come out in heat exchangers. You have to, and basically all things, is that you have to know that the steam has lost temperature, or it has lost energy. State 1 started here, and we went all the way down to subcooled. And that's by losing energy. And so you have to be careful by the way the signs are posted. And so that's why at the very end here, they flipped it as H2 minus H1, right? And that's why I did it as well, because you get a negative number there at the end. Although I didn't write a negative number, but you get the point. The point is that you have to be very careful with how these come out. And now I have a negative number. Look at that. See? And so, be careful with how they come out at the end. You have to know which fluid is taking heat in or which fluid is losing heat. That's what you need to know by looking at the question and reading the values. If one temperature, or if one fluid goes up in temperature, it means that that is the one that's gaining the heat. And since it is gaining heat, the other one is losing heat. So the other one's the heat transfer is negative. The one that is gaining heat is positive. Okay? Sorry for how long this took. I'm going to go ahead and stop the recording. And I will take